Let me welcome our guest speaker, and please help me welcome Dr. David Reitze to the Greenway Talks Online. David Reitze is the Executive Director of the Laser Interferometer Gravitational-wave Observatory laboratory, where he oversees a staff of 180 scientists and engineers. These are the people who built, who maintain, and operate the LIGO observatories at Hanford, Washington, and Livingston, Louisiana. Dr. Reitze holds concurrent appointments as Professor of Physics excuse me, at the University of Florida and Research Professor at Caltech. For 5 years, beginning in 2007, he served as spokesperson of the LIGO Scientific Collaboration. On the occasion of the first detection of a gravitational wave event, September 14th, 2015, Professor Reitze declared that the universe has spoken to us through gravitational waves. Now, 6 years and I believe, 10 detections later, we have come together today to hear about what the universe is saying, or perhaps chirping, to us. Please, Dr. David Reitze, thank you for joining us, and the floor is yours.
Oh, well, thank you very much, Steve, for that very warm and generous introduction. It's good to be with all of you. I think the last time I visited Palomar was about, 4 years ago, not long after the first detection. Since then, a lot has happened. So let me share my screen. Hopefully you'll be able to see this. Okay, so can everybody see the full screen?
Yes.
Great. All right. So actually, Steve gave me a nice title for the talk, The Gravitational Wave Revolution, Results and Next Steps. So these are the two, this is an amalgam of the two LIGO observatories, one in Hanford, Washington, the other in Louisiana. And the first thing you'll note, I recognize some of you on the call, so this won't be new to you, but for those who aren't familiar with LIGO, our observatories look quite different from conventional astronomical optical observatories. So what I want to try and do is start by explaining in one very terse slide exactly what gravitational waves are, and then I'm going to say a little bit about why we detect them. So they are colloquially known as ripples in space-time. They are a prediction of Einstein's general theory of relativity over 100 years ago. He predicted in 1916. It took us 100 years to actually detect them. And the reason for that has to do with the fundamental nature of this gravitational wave. The theory says that any accelerating object, be it an apple falling off a tree or a supernova exploding or black holes in orbit around each other, will produce gravitational waves, but the magnitude of those waves is exceedingly tiny. So there's one equation in this talk. This is it. And let me explain it. On the left-hand side, the delta L over L, that is the amplitude of the gravitational wave. Basically, what it says is that a gravitational wave manifests itself as it passes through an object or through a detector by basically changing the length by a small amount, delta L, over a baseline L. So another way to think about this is that if you want to, it's hard to measure delta L. So if you want to measure delta L, it's delta L over L, you want to make your baselines as long as possible. Now, the other terms in those equations have to do with the mass of the object, that's the big M. In this case, this would be for two orbiting black holes. The separation distance between them, that's R. How far away they are from you, that's D in the denominator of the equation. And then some constants which turn out to be really important. So if you calculate this for, say, some spinning black holes that are orbiting black holes that are maybe 30 solar masses, so 30 times the mass of the sun, the number you get is really small. It's 10 to the minus 21. And the reason for that is those constants. G is Newtonian, Newtonian gravitational constant. C is the speed of light. And the math just works out that way. So the point of this whole slide is to say that these gravitational waves are exceedingly tiny. Their amplitudes are exceedingly small, even for supermassive astrophysical objects. So it took 100 years to detect them, and 50 of those 100 years was spent trying to figure out how to make detectors that would detect gravitational waves. The rationale is really sort of a fundamental understanding of our universe. So why do we look for them, and what do they tell us? Well, they're a completely different way to look at the universe. So you've got Palomar, of course, the famed Palomar telescope, which looks at the universe in the optical. There are many other telescopes that look in, from radio to, all the way to the gamma ray spectrum. There are neutrinos. There are detectors that physicists have put together. We slam particles together in super large accelerators. This is the Large Hadron Collider at CERN. And by looking at the byproducts of those collisions, that tells us a lot about the fundamental nature of the universe. So, and then there's also cosmic rays. I didn't put a picture of that up here, but so that's basically, up until about 5 years ago, how we how we observe and probe the universe. Now, gravitational waves are completely new and unique probes, and the reason they're new, is because it took us a long time to detect them. The reason they're unique is because they probe different aspects of the physics of matter interaction. So they're produced by the most violent astrophysical events in the universe. I said they're produced by any accelerating object, but to make a detectable gravitational wave, you really need to be looking at ultra energetic events. They travel unimpeded through matter. That's both a blessing. In other words, they're pure carriers of information. They're not distorted. For example, like light, if you have, if you're on the other side of the galaxy, you can't, and there are dust clouds in between you and the thing you're trying to look at, you don't see it. Gravitational waves don't suffer through that, but it makes them harder to detect. They travel at the speed of light, and actually that was predicted by Einstein. Now we know it's true because we've actually been able to measure that. And they carry direct information about the relativistic bulk motion here. So what I want to do in the next couple of slides is sort of explain how LIGO works. So the picture on the right is the picture of the Hanford Interferometer in sort of the middle of Washington. And I drew those arrows on there to give you a sense of scale. So these interferometers are L-shaped objects, and I'll do a little video here in a moment to show you what exactly we're actually trying to measure. But I wanted to give you a sense of scale that the arms of the interferometers are about 2.5 miles, 4 kilometers. And so that's the L that we're trying to measure over, all right? Now, I said there's 2 of these interferometers. They're about 3,000 kilometers apart. It's interesting, you were talking a little bit about sighting at Palomar. Well, the story of how the LIGO detectors got sighted is itself a very interesting story to tell. It's not completely there are lots of pieces of it that aren't very public, but it's quite interesting. So how does it work? So let me show you this through a little video here. So these 5 things that you see on the left-hand side are, I'm not sure if you can see my arrow, but I'll try here. So this is a laser. That cylinder there is a laser. Oops. The little thing in the center is a beam splitter. It's going to take the laser light and split it into 2 equal parts. One of those parts will continue to propagate towards one of the mirrors. That's over here. Let's call that the X arm. And over here we have another mirror, which is located perpendicularly is the Y arm. And then here we have a photodetector. In this case, it's something that receives the laser light. So what we're doing is we're using the laser as really a very precise ruler, and particularly the wavelengths of the laser. So let me run the video here. So the laser generates very pure light. We'll split it. The color coding is just to distinguish between the two different arms of the interferometer. The light goes out, bounces back, recombines, and depending on the relative path lengths of the X and Y arm, you can either have negative interference, destructive interference to that output photodetector, or when a gravitational wave passes, you can actually have positive interference. So in this case, what a gravitational wave is doing is it's stretching one arm of the interferometer while it's compressing the other, and that's a fundamental prediction of gravitational waves. So what you see is it's actually modulating the interference and therefore producing a signal. And in this case, the wavelengths of light that we're using are about 1 micron. This greatly exaggerates the size of the gravitational waves that we're detecting. In fact, for the if you remember the 10 to the minus 21 I showed you before, you take 4-kilometer arms and you ask, okay, if I want to measure something on the order of 10 to the minus 21, what kind of displacement is that? And the answer is it's about 1/10,000,000th the diameter of a hydrogen atom. So it's about 10 to the minus 18 meters. So these are incredibly precise measuring devices, and they're incredibly sensitive. And that means we have to go to a tremendous amount of effort to isolate them from perturbations that could, for example, shake the mirrors, that could scatter light. There are many ways that you can change the signal on a gravitational wave detector that have nothing to do at all with gravitational waves. So the other point I'm going to make here before I move on to the next slide is that if you think about this at its sort of fundamental level, what's actually happening is, the laser light is being split, and what the gravitational waves are doing is changing the length between the beam splitter in the X arm and the beam splitter in the Y arm in opposite signs. But because it's changing the length, the light is actually it has to travel a little bit longer in the stretched arm, a little bit shorter in the compressed arm. And that's what leads to this change in interference pattern. Now, you might say to yourself, well, but the wavelengths are also changing because they're being stretched. And that is true, but that's not what we're actually measuring here is the time of flight of the photons. You can think about it. There are other ways to think about it also that are physically valid. But what we're doing here fundamentally is we're transducing a gravitational wave. So this is an antenna. It's basically picking up stretching space-time from gravitational waves that are produced billions of light years away, all right, and turning it into a signal that you can read out on a photodiode. Basically, it's voltage or photocurrent. So that's quite remarkable. A little bit more detail here, and I'm not going to go into any of the real core aspects of this, other than to say that this is a better representation on the left of what the interferometer looks like. And you see there's laser powers there, 45-watt laser. In the end, because of some of the tricks we play, it gets amplified up to about 200 kilowatts. You recognize the things that I showed you before. There's a laser, there's the beam splitter, there's the end mirrors right there. You see a lot of other mirrors, and those other mirrors are there to enhance the sensitivity of the detector. So let me just walk through some of quickly some of the subsystems here. So even though we only use 45 watts of laser light right now, we actually have a laser that produces 200 watts. My background, by the way, is laser physics before I got into gravitational wave astronomy. So I will tell you that this laser is a remarkable laser. It is the most, as far as I know, the most reliable and the most stable laser ever produced. And that you need that because you need the stability of the wavelength of the light to be able to make these precision measurements. And you can see a couple of people working in a very clean environment here. The power of this laser is so much that if a piece of dust gets on a mirror, it will actually damage the mirror as it burns. So the key to LIGO, actually, even though laser is fundamental to its name, is actually the seismic isolation system. The seismic isolation system is we do two things there. One, we actually have an active seismic isolation system, and you see one of our scientists working on it there. There are seismometers in there that measure the ground motion. So we want to basically keep the Earth from vibrating our detector. So they measure the ground motion, and then they actually feed back to actuators that move these massive platforms at very low frequencies to compensate for the motion of the Earth. We do that basically every mirror that you see in this in the picture actually has these very complex seismic isolation systems. The other thing I'll point out, it's not shown here, but essentially the entire interferometer after the laser is in a vacuum system, in an ultra high vacuum system, and we need to do that because we don't want any air or molecules scattering light. So continuing on with the seismic isolation system, this is a picture of part of what we call our quad pendulum suspension. So one of the best ways to isolate the mirrors, which are ultimately the things that the laser interacts with, are using pendula. So we have these very sophisticated, super engineered, that's one of the reasons LIGO works so well, pendula, and you can actually see there's fused silica. I don't have a picture of it here, but basically the mirror at the bottom, this is the mirror, the business mirror. This is the mirror that actually sees the laser, the test masses, as I call them in the left-hand figure. And they're suspended by 4 fused silica fibers that are about 400 microns in diameter. So each one of those fibers holds about 10 kilograms. The total weight or the total mass of the bottom mirror is about 40 kilograms. And that's the reason it's that mirror is so massive, is because you have to actually think about and control the fact that light itself has pressure. So there's radiation pressure from the light actually hitting the mirror. So that's quite so the bigger the mirrors, the better. So, and we do sophisticated carbon dioxide, CO2 pooling of the fibers. We weld them onto bond them onto the test masses. So ultimately, it is the test mass that sees the laser light. And here's a beautiful picture of an inspection of one of these guys. These are the world's most precise, as far as I know, these are the world's most precise figured mirrors. So the surface figure of these is much, much better. Maybe say much better because you're all astronomers or interested in astronomy, but they're much better than even the telescope mirrors that you have in Palomar or soon hopefully a 30-meter telescope, things like that in terms of their surface figure. So that's basically a walk through the interferometer itself. I want to come back to a little bit of again why this is such an important observational modality for fundamental physics and astronomy. And so you can ask questions. Gravitational waves are really the best way to probe gravity at its sort of inherent core. You probe gravity at its sort of most dynamical, strongest field regime. So you can ask questions. Does general relativity break down, and where does it break down? I mean, if we know, for example, that the theory of quantum physics, quantum mechanics, and quantum field theory, and now even into sort of superstrings, are fundamentally in conflict with, at the microscopic level, with general relativity. So scientists, physicists have been searching for years, decades, even longer, trying to take quantum mechanics and general relativity and put them together. And so far they've failed. And we don't know why they failed, but we do know that gravity is a very complicated force, and maybe by studying gravitational waves you could actually start to see where GR breaks down. Black holes, I'll say more about black holes much later. How does matter behave under extreme conditions? A very important one, which again I'll touch upon later on, is nucleosynthesis. So where do elements come from? Where do heavy elements come from? How do massive stars explode? By studying the gravitational waves that are emitted from supernova explosions, which I will say right now we have not yet observed. If we can observe that, we might get some better clues into the nature of the final instances, moments of supernova explosion. Of course, the universe is mostly made up of dark energy, and then it's also made up mostly of dark matter. You know, the stuff in the universe that we can see and account for represents a very measly 5% of all of what we know the universe consists of, and the rest of it is in dark matter and dark energy. So can gravitational waves shed some light on that? The answer is we think so, but we haven't yet that. And then, of course, because it's a new kind of modality, you know, when you invent a new instrument, a new way of measuring things, you're often surprised by, you know, we're going to see something that maybe we didn't even know existed out there. So this is what I would call the surprising aspect of developing new instrumentation. So maybe we'll see something that will really shake the paradigms of astronomy and astrophysics. So let me start by saying what the universe's revolution has taught us about black holes. And I think most people are very familiar with black holes, but here's a one-slide primer. Black holes are actually quite simple, even though the theory that predicts them, general relativity, is quite complex. Astrophysical black holes can be described by two quantities: their mass and their angular momentum. In fact, the mass, we don't know what's inside the event horizon of a black hole, but we do know that gravitationally the black hole behaves as it has mass at the center of that event horizon. In fact, general relativity says that there's no information in there. It's just that mass is sort of encoded in the curvature of the black hole as it goes down towards the singularity. So where do they come from? Well, we know they're stellar mass black holes. Basically, these are the residue of certain classes of supernova explosion. Not every supernova produces a black hole. There could be black holes formed in the aftermath of the Big Bang during the inflationary epoch. Fluctuations in the universe, the space-time curvature as the universe is growing could have produced black holes of some mass. We don't actually even know. Then there are intermediate mass black holes. These are the residue of supernova explosions of very massive stars, or and again, we now know this, that they can be produced in the merger of two lighter mass black holes. And then there are supermassive black holes. These are the black holes that are millions and even billions of solar masses in mass that exist at the center of almost every galaxy. And where do they come from? Well, they were formed, where they formed the universe, where they formed at galaxy collisions, where they seeded by sort of a chain reaction of lower mass black holes, all sort of accruing and basically accreting onto the big black hole. We don't know that yet. Now, how do we study them? Well, I think one of the biggest and most recent breakthroughs was the Event Horizon Telescope result of the supermassive black hole at the center of M87. So this is an image that is now famous of what's known as Pauehi. Pauehi is the Hawaiian name that was given to this black hole. And what you're seeing there is basically the shadow that the radio emissions cast around that center dark spot, which is the black hole itself. By far, up until gravitational waves came along, the most information, by far the best way to study black holes was to study the emission of X-rays and other kinds of optical emissions or electromagnetic emissions from what are known as low mass X-ray binaries, where you have a star locked in a binary system with a black hole, and the star basically is shedding material exceeding its Roche lobe and basically accreting onto the black hole, and that process and the matter accelerates. It produces basically X-rays that get studied. And then of course we have gravitational waves, and let me go back and start that. So this is a simulation. That the data that you see there is the famous data from the first gravitational wave detection on September 14th. The simulation that you see is actually produced by extracting the astrophysical parameters from the data. So this was produced by Kip Thorne and Saul Tucholsky and his group. And what we observed were two black holes that actually sort of orbited around one another and then merged into this single massive black hole and emitted this burst of gravitational waves. So these are the kind of the ways that we study them. Now let me come to a point that Steve raised earlier about how many detections that we have. So let me start with this slide. I really like the way this slide presents the data. So all those little purple dots, don't worry about the x-axis. Don't worry about the horizontal axis. The vertical axis is the one that matters. So what you see there are masses, 1, 2, relative to the mass of the sun, so stellar mass black holes. And what you see in this diagram are what we call EM black holes. So these are black holes that have been discovered through that, basically by studying low mass X-ray binaries. And if you count them up, you'll see there's maybe about 25 or 26 of them or something like that. Some of them have question marks, and the reason they have question marks is because we're not really sure. The data isn't super compelling that suggests it's a black hole. The one actually at the bottom is quite interesting, the one between the 2 and 5. The reason that one's interesting is because we haven't confirmed yet that we've seen any black holes lower than 3 solar masses. So by measuring, if you will, the spectrum of the black holes, that tells us something a lot about their formation and things like that. Now let me show you what we've done with gravitational waves. So to answer Steve's question, we now have about almost 60 detected events. We just came out we're about to come out with a paper where we present all these events. And so these light blue black holes are the black holes that LIGO and our partner Virgo have detected. And you can see that there are many interesting things to this. First of all, the black holes that we see tend to be more massive than the black holes that are seen in E&M telescopes. And now they're not the supermassive black holes that that are at the center of the galaxies. They're much further away. So the electromagnetic black holes are mostly in our galaxy, whereas some of these black holes, in particular the most massive one at the top, there are out billions and billions. I think this one is about 7 billion light years away from us. So these are black holes that are actually, we're seeing in sort of starting to see at cosmological scales. Now, by studying the mass spectrum, and each by the way, the arrows represent the 2 black holes that are merging into one black hole. Of course, is when LIGO detects and Virgo detect a black hole merger, it's a sort of a 3-for-1 detection. We see the 2 black holes and can get information about the 2 black holes that were colliding to produce the final black hole, and we get information about that also. So anyway, so this just sort of gives you a sense of the fact that for studying stellar mass black holes, gravitational waves are really a very powerful tool. And it took 40 years to populate all of the purple dots, the EM black holes, and it's taken us about 5 years to produce. So if you count them up there, I think there are about 150 of those black holes there. I'm going to focus on 2 of them because I think these are really interesting ones. I'll start with the one at the bottom where you actually see the orange dot. What is the orange dot? The orange dot is a neutron star. All right. I'll say more about neutron stars later, but this particular merger was the merger of actually it's not this one. It's all right. The particular merger of a neutron star and a black hole into a black hole. So we call this a mystery merger. This was from our latest run that ended last year. This was detected on August 14th, 2019. It's about 800 million light years away, so it's not that far, relatively speaking. It's a unique event because the mass ratio of the objects that merged were quite different. Was quite different. Typically, we see black holes that merge with about the same mass, maybe within a factor of 50% or something like that. But here we saw something that was 23 solar masses merging with something that was 2.6 solar masses to produce a slightly heavier or slightly more massive black hole. The thing that's puzzling about this is that 2.6 solar mass object. We don't know what it is. It could be the lightest black hole ever observed. It could be the heaviest neutron star ever observed, but it falls in this sort of gray area. We call it a mass gap between 2 and 3 solar masses, where we just don't know enough to be able to assign with any confidence what this is. So this is, again, this is another thing that I think is intriguing, because you start to see things that you don't understand, and it probes more study. The data, I wouldn't say the data, I would say theoretical considerations suggest that it's a black hole, but we can't say that with any certainty. So, all right, the next one I want to show you, I think, is even more interesting. It's probably in my own mind, probably one of the most amazing results that came out of our last observing run. And it's a movie, and I'm going to start the movie, and I hope you can hear the narration. Steve, if I could ask you to confirm that. Do you hear the narration?
I did not hear the narration, no.
All right, I'll narrate it for you. Okay, all right. So we call this the impossible black hole. So these are 2 black holes that are merging to produce intermediate mass black holes. This object is the most massive object we've ever seen. This is the first intermediate mass black hole ever detected, 142 solar masses. But the really interesting thing is that this 85 solar mass black hole shouldn't even fit. And it has to do with formation dynamics. So light stars explode if they're less than, they can move black holes up to about 60 solar masses. And heavier stars, basically because of the nature of the explosion dynamics, completely blow up. So you shouldn't see black holes between about 60 and 130 solar masses. And then the most massive black, or the most massive star, actually compress directly to a black hole. So in this particular case, where did the 85 solar mass black hole came from? Now I'm just going to move to the next thing, because it's hard to talk over the narration. So to sort of summarize here, the 2 things that were very interesting about this event are, one, this supermassive this intermediate mass black hole is the first confirmed observational intermediate black hole ever observed. And you might say, well, why is it an intermediate mass black hole? And the answer is, we draw that line at about 100 solar masses. But the other interesting part of this is that 85 solar mass black hole there, and that's the black hole that, because of the conventional formation dynamics of black holes, shouldn't have been produced by a supernova explosion. It's just in the wrong place massively for that. If it were lighter, it would be fine. If it were heavier, it would be fine. So where we think these came from, or where, particularly the 85, but also possibly the 66 solar mass black hole, is that these are actually themselves the products of earlier gravitational wave mergers. So we would refer to these as generation 2 black holes, and then they of course merge to produce this this intermediate mass black hole. And so this is the first hint that and by the way, we study the fact that the black holes are spinning, and there's tantalizing evidence in the waveforms to show that it could be true that these were actually 2nd generation black holes. So what you're starting to see here is sort of this chain reaction that could lead to, for example, supermassive black holes forming in a galaxy. Again, we don't know that. We don't know definitively that this is the case. We'll have to study and see more of these, but it really is starting to be subjective, that we're starting to get understanding about how these black hole systems can form. And now let me touch upon Palomar directly here, because I think this is really exciting. I'm going to say more about this in a moment, but when we detect our gravitational waves, we actually send out what are known as astronomical alerts. So we rapidly identify that we have a gravitational wave signal. We can say something about where it came from on the sky, and then astronomers can follow up basically pointing their telescopes, be it ground-based telescopes or X-ray telescopes, gamma ray telescopes in space. They can repoint to try and find the signal. And I will say it's a difficult game, and you'll see why in a minute. But Matthew Graham, a colleague of mine at Caltech, and his group using the Zwicky transient factory found a possible counterpart to these two black holes merging together. And the question mark is important because you can't say with 100% confidence that this counterpart that they saw was from the merger of the black hole. And of course, black holes are by definition non-emitting, and they suck everything around them into their singularity. So where did the light come from? So the speculation is that if indeed this did come from these two black holes, it's consistent with the fact that these black holes were in a very gaseous environment, and that basically they didn't actually see the signal at the time of the black hole merger. They saw it after that. And so the working theory here, about 25 days after, and the working theory is that the black holes, because when they collide with one another and they have spin, they can actually give a kick to the final black hole. So it's basically a conservation of momentum. And the black hole actually then goes into the accretion disk and basically produces a bit of a shock. And that shock is what the emission is from. So this is a really tantalizing result. I would say that, if you ask, the astronomy, the time domain astronomy community, whether they completely believe it or not, you'll get a spectrum of answers. But it's interesting and subjective that this is another place where we might be, starting to see some new kinds of astronomy that we haven't seen before. Now I'm going to turn to neutron stars. Let's see, I'm not on time here. Yeah, neutron stars are quite different from black holes. They're also produced in supernova explosions. They're less massive. So conventionally, a neutron star is somewhere between 1.1 maybe and 2 or 2.5 solar masses. And as their name suggests, they are made up mostly of neutrons. So you can think of them as sort of giant atomic nuclei made up mostly of neutrons that are massive, that have more than the mass of the sun, and they're incredibly dense. The density of neutronium, if you will, if you take a tablespoon of neutron out of a neutron star and you were to weigh it on the Earth, it would weigh about 1 billion tons. That just reflects the fact that this is basically pure nuclear matter. So these things are ubiquitous in the galaxy. There have been thousands and thousands of discoveries of neutron stars over the past 50 years through radio telescope. They were first discovered actually by Jocelyn Bell in the UK. They're interesting because when they collide, they contain matter. So the idea that's come about, and I don't know who coined the term, but I like it. It's called multi-messenger astronomy with gravitational waves. So the messengers in this case are information carriers, gravitational waves, photons, cosmic rays, neutrinos, light across the electromagnetic spectrum. So when you have two objects that are massive and compact and moving relativistically around one another and they collide, they're going to produce gravitational waves. In fact, the gravitational wave signals will even happen before the collision, because in the in-spiral phase, as these two objects are dancing around one another, when they collide, they should produce all kinds of light. They could produce cosmic rays. We haven't necessarily seen that yet, and they could produce neutrinos. So the idea here is that by studying all these things, you get call it a concordant picture of the physics behind binary neutron stars, and also it starts to give us clues and understandings of where high energy gamma ray events come from here. So now let me talk a little bit about the challenge of localization. When I was talking about the black hole E&M possible counterpart, I said that we can localize these gravitational wave events on the sky. And the way we do that is by having multiple detectors. So we have the two detectors in the US, and then we work very closely with the VIRGO gravitational wave detector in Italy. There's a nice picture of it in the upper left-hand corner. And the idea is that if a gravitational wave signal is produced, it travels at the speed of light. And because these detectors are located in different places on the Earth, there are slightly different arrival times, measured in milliseconds, a few milliseconds. And so we can time the arrival of the gravitational waves very precisely because we can measure their wavelengths. So we know by measuring their wavelengths within small fractions of a millisecond when they arrived. And so by constructing basically the possible loci or positions of the signals that could produce the signals that arrive at the gravitational wave at the same time, you can get a sense of where the object that produced the gravitational wave is. And so it's basically triangulation. That's how it works. So, and the important point is to do this well, you need at least three of these detectors because you need to triangulate. It turns out you do get some information from two detectors, and you can, but one detector, the gravitational wave interferometers or the analogy we give is they're more like microphones in many ways, actually. So they see signal, they have very limited angular resolution. The way telescopes have super good angular resolution. So, all right. So here's our network today. The current detectors in operation are the two LIGO detectors at Hanford and Livingston in the United States. We have the VIRGO detector I showed you. There's another detector called Geo 600. It's a smaller detector in the term that it has less arm length, so it's not sensitive enough to participate meaningfully in some of the events, but it's actually a lot of the technology was used by the VIRGO and LIGO detectors. Very recently, in the last, just last year, the Kagra detector in Japan came into being. It's exactly the same kind of detector as I showed you, interferometric detector. It's an underground detector. So it's a little bit, actually, it's better isolated from seismic noise. And then there's a detector that's actually now starting to be under construction in India, which is basically a replica of the two LIGO detectors. So, but for the slides that follow, everything that I'm going to talk about is going to be about the two LIGO US detectors in VIRGO. So, yeah, to sum up gravitational wave localization, it's complicated. And the reason it's complicated is it depends on a lot of factors, some of which you have control over, many of which you do not. So first of all, it depends on the number of gravitational wave detectors online. I said you need 3. It turns out if you have 4, once Kagra did not run with us in 2003, we expect them to run on the next run. 4 will be better. And LIGO India even provides more. And where they are, it depends on where those detectors are. The further away they are, the more you have a distribution off of a single plane, the better. It also depends on the localization of the source in the sky. That becomes less important if you have more detectors. But for 3 detectors, it's really important. The distance to the event. The closer the event is, the larger, or to use the sound analogy, the louder the signal. It also depends on the parameters of the source themselves. And that also is a larger signal constraint, that the more massive an object is, the black holes that we see are the most effective radiators of gravitational waves. And then the other thing that matters is whether or not we see it in time coincidence, and more importantly, in spatial coincidence with other detectors. So this, I'm going to show you 2 slides here. This is the sky map. So you can think about this as basically projecting the sky a two-dimensional map of the mystery merger that I showed you before. And you see the two off here, you see two dots. So these represent the outer contours represent the 90% confidence area. So in other words, we're 90%, we believe with 90% confidence that the event that produced the gravitational wave was in, one of these two islands on the sky. If you want a little more precision with a little less confidence, you go into this little dot right here, and that's 5 degrees. So from an astronomical perspective, this isn't so great. Telescopes typically have arc-minute or even arc-second resolution, and the best that we can do, and that has to do with the fact that these gravitational waves are much longer wavelength sources, is on the order of a degree or a few degrees here. So this is a good one. Here's a not so good one. This is from another binary neutron star merger that we detected in 2003, and in this case, you can see that almost a fifth of the sky is lit up. So it's challenging if you have that much sky to cover to try and look for a gravitational wave signal, or an optical signal, if you will, an optical counterpart that came from a gravitational wave signal. It's going to be really challenging in this environment. So the smaller these error boxes, the better off you are. But it turns out we got really lucky, and I've become a believer in never discount the power of luck in scientific discovery. So the first gravitational wave signal that we ever saw with an electromagnetic counterpart from a binary neutron star was GW 170817, August 17th, 2017. I'm going to show you a little bit of video here, but when I start the video, you see a bunch of different bands. So the blue bands that say Fermi integral or Fermi are the error boxes that were produced by not a gravitational wave, but by a gamma ray burst, and a really interesting gamma ray burst that happened almost at the same time, almost coincidentally, with the detection from LIGO VIRGO of a gravitational wave signal. And you can see the bananas here, the sort of the dark green ellipses or bananas are the sky map with LIGO only data. In other words, how well you'd be able to localize the signal in the sky with only LIGO data. Whereas if you add Virgo, you see that the sky localization increases dramatically. And now let me tell you the first lucky thing. The first lucky thing is that a month earlier, Virgo was not running. In fact, we were thinking, the collaboration was thinking about, should we continue to run and wait for Virgo, or should we shut off our instruments? We were originally planning to shut off our instruments in June of 2017, and we chose not to do that, and that was by far the wisest decision I think we've ever made, because on August 17th we saw an event, and let me now play the movie. If you zoom in on that, that's about 28 square degrees. We sent out an alert. Astronomers, those little dots there are galaxies. Astronomers zoomed in and found, after about 11 hours after our event, zoomed in on this galaxy. This galaxy is NGC 4993. It's about 140 million light years from us, which is very close from a gravitational wave perspective. And a number of telescopes, including ZTF, were able to see a transient event, and that transient event is marked by those blue arrows. The astronomers designate them different from the gravitational waves. So this is SSS 17A, and that blue dot wasn't there before the gravitational wave signal was detected. So at this point, what we've got is we've got a gravitational wave signal. Independently, we have a gamma ray signal that came at the same time coincidence. And now we have evidence from not just this telescope, but 6 independent telescopes that this transient that was found in a galaxy that was within the distance that the gravitational wave signal could have been produced. So this was a home run. This is the first multi-messenger astronomical event ever with gravitational waves. And the other thing you can see, and this is an important clue to what's really going on here, is that the signal from this is called a kilonova. The signal from this kilonova is actually diminishing and shifting towards the red. So when it was first seen, 11 hours after the detection, it was blue. After about 4.5 days, it shifted to the red. And that, by following the spectrum, astronomers follow the spectrum, that gives you powerful clues. So this was led to, I would say, one of the most remarkable astronomical follow-up campaigns in the history of astronomy. It probably rivaled and maybe even exceeded supernova 1987A. So we sent out our alert, and approximately 75 ground-based astronomical observatories all over the world, you can see those blue dots there, followed up this event. The event was first discovered in Chile, but it was also by the Swope and Magellan telescopes. It was also discovered independently by a number of other telescopes, and then followed up by not just these Earth-based observatories, but also a lot of the space-based observatories, such as NuSTAR, XMM Newton, Swift, Fermi, also were able to see this event. And let me start with the data, and then I'll show you the signal. No, let me actually not do that. Let me show you the signal. So I'm going to show you another movie here. So this is basically an artist rendition. There's no physics in this, of these two neutron stars that were colliding in that galaxy, and they produce, basically, when they collide, it's spectacular. They produce a burst of gamma rays that comes out perpendicular to the orbital plane of that. They produce huge clouds of very dense neutrons that undergo rapid atomic or nuclear processes, what's known as R process nuclear synthesis, capture to form heavy nuclei. And the matter actually collides with interstellar medium. So that's what those purple sort of mushrooms are up at the bottom and top of that. And the data is really quite cool. So the bottom of the graph on the left is the gravitational wave signal. We plotted on the y-axis is frequency, on the x-axis is time. So you can actually see the objects are spinning faster and faster as they get, or the orbits, going faster and faster as they decay closer and closer to one another. And then the three panels above that are the observations of the gamma rays, which were done independently. And actually, we did not know we had this signal until about an hour and a half after it came in, because one of our detectors had a glitch in it, and we had to actually go to great effort to get rid of that glitch. Whereas the gamma ray signal was known before we even knew we had a gravitational wave signal. So the time difference between those the merger and the GRB start is about 1.7 seconds. So using that time difference and using the fact that this object is about 140 million light years away means you can measure the speed of gravity relative to the speed of light. And it turns out to, within experimental, they're about the same. Now, the other interesting aspect of this, and I don't have the data to actually show you because I don't want to spend too much more time on this, is that this collision was the first solid evidence of a theoretical conjecture that's been around for a while, namely that heavy elements, those are elements that are in the red lines in that periodic table that I showed you, are predominantly produced in the collision of neutron stars. So very light elements are produced in the Big Bang. Mid-range atomic number elements are produced in supernova explosions, but the heavier elements are mostly produced in these neutron stars. And until observationally, we couldn't say that with confidence, but the theory predicts very accurately how you would be able to extract from the spectra of the observational, the spectra of the kilonova, and fitting it to certain theories that you actually produce this. And so the thing that got everybody's attention about this was that this is where gold comes from. So chances are that if you're wearing any gold jewelry or something like that, it was probably produced in the collision of two neutron stars billions and billions of years ago. So this it doesn't mean that all of the source of these heavy elements comes from that, but there's strong evidence now that a lot of it does. So this was a remarkable event. The other thing that you can do with this event, and I'm not showing any data on it, is you can actually measure the Hubble constant with this event. We were able to do that too. So I'm going to conclude with just a couple of more slides on where the future of this field is. What I've talked about are what are really high frequency, if you will, gravitational waves. These are gravitational waves that go from about, say 10 hertz to a few kilohertz. There are higher frequency gravitational waves, of course, but it's hard to see how they would be produced in any way that's detectable or by astrophysical sources. So this is sort of the spectrum of gravitational waves. On the top, you see the kinds of astrophysics you can look at, and on the bottom, you can see the detectors that are used for them. And as you go to longer and longer wavelengths, you start probing different kinds of astrophysical objects. So with space detectors such as LISA, I'll talk about in a moment, you detect more intermediate mass, heavier intermediate mass black holes. You can probe phase transitions in the cosmos. Using something called pulsar timing, you can actually detect the merger of supermassive black holes when galaxies collide. And ultimately, even the Big Bang itself produced a residue of gravitational waves that's imprinted itself on the microwave background of the universe. You can actually use different kinds of detectors to be able to do that. So this is the entire, you can think of it, this is the analogy to electromagnetic spectrum. This is the gravitational wave spectrum. So the LISA space laser interferometer space antenna is a project that's we're very excited about in the ground-based community. It's going to be launched, we hope, in 2034. It's got a green light from NASA. It's had a history of development, but it's only after really 2015, after the discovery, that it was green lighted for launch. So this will go up in 2034, and this will form sort of the next one of the next nodes in the gravitational wave spectrum. And then finally, now that we know that we can detect gravitational waves, and we know how to build gravitational wave detectors, the plan for the ground-based community is to actually build even bigger detectors. So in Europe, they're pursuing something called the Einstein telescope, which is a very, very sophisticated detector. It's actually 6 interferometers, all co-located in a triangular configuration underground. On the US side, we're going a slightly different route. We're going to basically take the LIGO detectors that we know how to operate, and we are going to basically make them 10 times longer. So that picture there looks like a moonscape. It's actually could be somewhere in the salt plains of Utah, or perhaps in White Sands, or perhaps somewhere in Idaho. But if we can we have to find a place to put it. But if we can do that, we think that both of these detectors actually will be operating in the 2030s and beyond. And the key to making them more sensitive is just that they have longer arm lengths. So basically, for the LIGO version, which we're going to call Cosmic Explorer, we'll get a factor of 10 increase in sensitivity because we can make the arms 10 times longer. And this is really one of the amazing things about gravitational waves, because of the nature of how we detect them. These detectors should allow us to see basically the entire universe in gravitational waves in the frequency band that we look at. So we expect to be able to see every a black hole merger that hasn't yet, or that is still coming at us and inbound over the entire universe. So we can go well beyond where even galaxies form. We'll go out to redshifts of 10, 20, maybe even 30 or 40. I mean, because the sensitivity of these things is so great. So I'm going to stop there. I hope I haven't gone too long. And the summary is that the gravitational wave future is quite spectacular, and I expect that we will be hopefully making more exciting detections. Right now, we're in a downtime. We're talking about at the beginning of the discussion. We are in the process of making major upgrades to our detector, and we're having to do the same kinds of things, learning how to work in close proximity, in a way that keeps people safe. But we've done that, and we hope to go back online probably in about a year and a quarter or so with our next run. So I think I'll stop there. I will basically say, this is the work that I'm talking about here is the work of thousands of people. The LIGO lab is Caltech and MIT, but we also work closely with the LIGO Scientific Collaboration and Virgo. And then, of course, I always have to note that we do this work because the U.S. taxpayer graciously funds us through the National Science Foundation, and so that's what makes this all happen. So I think I'll stop there, and I'm happy to take questions.
Dr. Reitze, thank you very much. That was a wonderful presentation. We have time for questions. There are a couple of things in the chat. First of all, Scott Dixon, you had a question.
Mm-hmm.
Scott?
Yeah, I think it's in your first slide, you showed an equation with
Right.
D in the denominator, not D squared. And so I was wondering why the amplitude of the motion, delta L, doesn't go like 1 over D squared.
It has to do with the nature of gravitational waves and the nature of the detector. And in fact, yeah, so indeed, the gravitational wave signal decays as 1 over D, not 1 over D squared, which is a really fundamental advantage that gravitational wave observatories have over astronomical observatories. First of all, we're a coherent detector. We can actually measure the wave. We directly measure the amplitude and the phase of the wave. So right there, that tells you, that we do things a little bit differently than E&M detectors. But if you look at the propagation of gravitational waves from a source, the signal just naturally falls off as 1 over D. And that's why, by the way, that these next generation detectors that I showed in the last slide, Einstein Telescope and Cosmic Explorer, can see so much further than, in one generation, we're going to go from seeing, out to a few billion light years all the way to the edge of the universe because of that. So,
But the gravitational wave is transporting energy away from the source.
Sure.
And the area over which the gravity wave is covering is a sphere, which of course the area of the sphere increases with D squared. So at the same time, the delta L is only going down like 1 over D. The energy density must be going down like 1 over D squared, or is that wrong too?
The energy density is basically the square of the strain of the gravitational wave. So the energy density is going down as 1 over D squared.
Okay, now I feel better.
But we are measuring, yeah, but we measure the amplitude correctly. So the energy density falls exactly the same, yeah, as you would expect. But because we measure the amplitude, that's the signal. So.
Okay.
And also, Julie Wu, if you're still here, you had a question earlier. Julie?
Well, it's my husband's question. So that ask.
Yeah, we just wondering why closer is better. So does it mean that these gravitational waves are losing amplitude as they travel? And if so,
yeah,
how do they lose amplitude? Do they interact with matter or something? It's just a very naive question.
Yeah, it's a good question. I mean, it relates actually to the question that Scott asked, but because the gravitational, all right, the signal to noise, that the signal of a gravitational wave basically falls off as 1 over the distance. So if I have an object, a gravitational wave event, and I'm a distant distance, I'll just pick a number, 1 light year away from that gravitational wave event, I'll measure a signal. And more importantly, I'll measure a signal to noise ratio. And what that is depends on whether the object or black holes are, or neutron stars, or whatever the source is. If I double the distance, if I take that same event and move it out by a factor of 2, because of the propagation dynamics that we talked about with Scott's question, the signal will fall off by a factor of 2. The signal is 2 times lower. Now the noise in our detector doesn't change, and that's the important thing here, is the signal to noise. So if you were to say we have a threshold, which is, it's not a, I wouldn't say it's a hard and fast rule, but it's one we like to use. We call our detections confident detections when they have signal to noise of a little bit better than 6. And if you were to say, okay, suppose I have an object, all right, that's a certain distance away that has a signal to noise of 6. If I move that object twice as far away, it's a signal to noise now of 3, because I've doubled the distance, I've halved the amplitude of the wave. And I don't see it anymore because it's now below my threshold for a confident detection. So when I say closer is better, I mean the signals are just bigger, all right, and they scale exactly as the distance. I think that answers your question, Ray. I hope it does.
I've got a wavefront question.
Go ahead.
And by the way, this is Ken Searcy, and
Yeah,
thank
hi.
you so much for coming to our banquet a few years ago.
Good to see you. Yeah, how are you?
Oh, just fine.
Good.
We're all crowing about receiving 2 shots, and we feeling like we're in a new category of life. You said that matter doesn't affect the gravity wave.
Yeah.
However, I would expect the gravity wave to follow the distortion of space and time caused by matter. And so therefore, you would expect that to affect the wavefront of the gravity wave.
Yeah.
And do you think you'll ever be able, do you see that factor, and do you try to model it, or do you think you'd ever be able to measure it?
Yeah, so the question you're asking is one that we're asking too. So to basically, yes, it's exactly correct. When you have an event out there, if there's a distortion of the gravitational field from a galaxy or a cluster of galaxies or something like that, the gravitational waves will be lensed. They will actually change their direction as they go through that. So that's gravitational wave lensing. Astronomers use weak lensing of light and strong lensing of light. So we believe, I mean, it's a fact that gravitational waves, wavefronts will be distorted as they go around massive objects. They will not be absorbed. That's the thing that makes them sort of much easier to see than light in many cases. We are looking, actually, I was just on a call yesterday, or not yesterday, a couple of days ago, where we're looking at data to see if we can actually see gravitational wave lensed events. And if you do, you could actually, it's quite interesting, you could actually see the same event, but you could see it delayed by some period of time because the lens, lensed path takes a longer time to get through, to get to us. But so far we haven't actually seen anything like that yet. But Ken, you're exactly right. That is a thing that we look for, and hopefully we'll see it someday.
Thank you.
Other questions? We do have a couple of questions in the chat, but if anybody wants to ask something now?
Sure. This is Antonio. Thank you very much. It's a very interesting talk. Still learning about the subject. I'm just curious, are any of these places, can you visit them, or are you discouraged from visiting them?
We would love to have you visit when they're open again.
When they're open? Yeah, that's true. When they're open.
Right now, so right now we do have both observatories have education and public programs. But right now, because of COVID, there are no observatory visits. We don't know when things will change. If the pandemic calms down, it may be that we'll open up again in the fall. But at this point, it's hard to say that. But yes, absolutely. And if you go, I should have put it in the slides, but if you go to ligo.caltech.edu, you will get all kinds of information about the outreach programs that we have there and things like that. But no, we encourage people to come and visit. We have the visits are not unstructured. There's only certain days you can go and things like that. But yeah, you can get on a tour.
So I had a couple of clarifying questions as I was listening to some of the things you said. You said signal to noise 6. Is that like 6 dB or?
No, it's just a ratio. It's a ratio. If you look at the data stream and you say, there's a noise and there's an RMS value for the noise, and you look at the signal and there's an RMS value, or there's a value for the signal. Now, the way we search for the data, and I didn't go through it, is we use match filtering. So we actually, one of the nice things about general relativity is that you can, it tells you how to calculate what the waveforms actually look like. So I don't have my slides up, but if you remember when I was talking about black holes, I showed some data very briefly that showed the waveforms there. And we can actually calculate for a given object, a given binary black hole merger that has certain masses in it, we can actually calculate what those waveforms look like. And so we cross correlate the data with I think right now we're up to almost 1 million waveforms. So every second of every gravitational wave event, or every stream, the data that gets streamed goes into a computer where it's cross correlated with 1 million times massive. We have what's known as massively high throughput computing that rapidly searches for those data. So the signal to noise there is basically the ratio of the cross correlated signal to the noise.
Okay. And can gravitational waves be like absorbed or attenuated if they go through some object or not?
Again, we rely on general relativity for this, but the answer is no, because what they are, remember, gravitational waves are basically fluctuations in space-time themselves. So, they're actually very hard to comprehend, right? I mean, people, when you think about electromagnetic waves, for example,
Right.
you think, well, they're traveling through a medium, but the medium is nothing. The medium is space. Well, it turns out space is something, and general relativity makes very precise and testable predictions about how space curves and how space stretches when you have dynamics going on there. So in fact, the gravitational waves are propagating space-time themselves. They do not interact with matter. Matter interacts. Okay, so the way to think about general relativity is to basically say that where does space-time curvature comes from? It comes from putting an object, a massive object, in an empty space. So if there were no objects in the universe, space would be pretty boring. It would be what's called flat, Cartesian. All right. As soon as I put an object in there, all right, it curves the space. Basically, the mass of the object, and this is the fundamental, premise of general relativity, is that mass and energy and space and time are equivalent to one another. They're not equal, but they're basically, you can write down an equation called the Einstein field equations that relates mass, energy, space, and time. And the way that people think about them, and I'll quote John Wheeler, who was one of the preeminent general relativity theorists, is that general relativity can be thought of as space tells matter how to move. All right, so objects in a curved space, objects follow straight line motion, but when you have curved space-time, that a straight line isn't a straight line the way it is in a Cartesian coordinate system. It could be a curved line as it is in in orbit. So the orbital dynamics of any system are basically objects doing what the space tells them to do. All right. And then the other aspect of that is space tells matter how to curve. I'm sorry, matter tells space how to curve. So there's this back reaction, but the back reaction is not sufficiently, there's not sufficient coupling to be able to say that you can convert gravitational waves into mass and energy. It's just the way they interact. So having said that, if we actually look for, in the data, we look for deviations from general relativity. And one of the ways we try and do that is by looking at deviations in the waveforms relative to what general relativity predicts. So some people call this dispersive gravity. If you were to see that the waveforms do not have the frequency dependence that's predicted by general relativity, we might be able to say that, oh, there is some coupling between matter and space that general relativity didn't capture properly. So, I've learned after talking to a lot of experts in general relativity, and just in general relativity is a very solid theory. Most people don't believe, even gravitational waves, they don't believe we'll be able to actually put a dent in it. But we look, because if you see it, it's a huge, would be a huge thing, right? So our tagline when we first made a discovery was, Einstein was right, that because he predicted gravitational waves. If we see the kind of thing that you're talking about, the tagline would be Einstein was wrong. So
Thank you.
Catherine Height, you had a question in the chat.
Yes, I actually just learned that gravitational waves travel at the speed of light, in the last bit now. And then I wonder, why is it that LIGO can detect the gravitational waves first and then light is detected after if they're going at the same speed?
Yeah. So think about this binary neutron star event. So let's go back in time. All right. The neutron stars are, in fact, it turns out that most stars in galaxies form in binary systems. All right, and they're orbiting around each other very slowly. And as they go forward in time, the orbit is decaying ever so slightly because they're emitting gravitational waves. So energy is leaking out of that binary system through the emission of gravitational waves. All right. Now let's think about maybe not stars, but neutron stars and black holes. All right. What happens is the orbit decays. The orbital frequency, the orbital radius gets smaller. The orbital frequency goes up, and in fact, the something known as the periastron shift, basically the point at which they come through closest approach again, starts shifting forward and forward in time. All that is to say that as the system plays out its dynamics, it's emitting gravitational waves. Now, let's think about black holes. They're not emitting light at that point. Let's assume there's no matter anywhere else around. So it's just two black holes in isolation. They're not emitting light at that point. All right. And when they collide, they just go behind. So now let's think about two neutron stars. The neutron stars are emitting light in the unconventional sense. They're emitting radio waves. And in fact, people study binary neutron star systems through long duration, years, decades of following a neutron star population. But in this case, the light we're talking about is the light that's produced right at the collision, the gamma rays and the kilonova, the optical light. And so in this case, the sequence of events is right, say, a minute before these two neutron stars collide. All right, they're orbiting around one another really rapidly, and I didn't tell you the frequency, but these things are orbiting around one another 1,500 times a second. So picture that. These are objects that are, more massive than the sun, that are very compact. Their radii are about 25 kilometers. All right, and they're moving at about a third of the speed of light. So these are really, out there in terms of relativistic astrophysics. All right, and they're emitting radio waves, but we're not paying attention to that because we don't see them. All right, so they're emitting gravitational waves. The gravitational wave, as the orbit comes in, there's this crescendo boom. All right, and once they collide, the gravitational wave radiation is mostly over. It's not completely over. In fact, we think we might be able to in the future to see the formation of a black hole. What happens after these collide. But at the point where they collide, that's when the light turns on. That's when the gamma rays turn on. That's when the optical stuff turns on. So it's a question of just time scales here.
One's
So,
just before the other. Okay.
Exactly. So I
Thank
hope that answered your
Yeah,
question.
thanks.
Great.
I've got a question for you.
Mhm.
Since you don't know the amplitude at the source a priori, and
Right.
you don't know the unredshifted frequency of the gravitational wave, how do you derive a distance to the source? It seems it could be a degenerate problem, little masses close by, big masses far away, that kind of thing.
And indeed it is. So the first thing to say, and when I give these talks, sometimes I'm good about pointing this out. This time I wasn't. The precision with which we can estimate the parameters of the gravitational wave is really quite poor. All right. So when we quote masses, the intermediate mass black hole was 142 solar masses. Well, it could have been 160 solar masses, or it could have been 120. That's basically the confidence level, which we have. So the precision is poor, and the reason that is because the gravitational waves are, the signal to noise isn't that high. There's a lot of noise on them. But to answer your specific question, all right, there are two things that we detect in gravitational waves. Each detector detects an amplitude, detects the frequency and the amplitude. So the gravitational wave signal starts out with lower frequencies, so it's like this, and then it gets to higher frequencies, and the amplitude goes up. Because you can calculate using general relativity what the source is, what any given source would produce, and by doing that cross correlation, you get the information that the frequency of merger was 300 hertz. That tells you that tells you something about the masses, right? And the phase of the gravitational wave signal gives you very precise information about the source. That's called the chirp masses. Now you asked about the distance. The way we get the distance to the source is actually encoded. The luminosity distance to the source is encoded on those waves to the precision that we can measure them. So by just measuring the frequencies of the waves and the endpoint merger, that tells you essentially what the source is. All right. But then you measure then you look at the amplitude of the wave and you say, all right, we know the source was 2 massive black holes, 10 solar masses, and the amplitude of the wave is 10 to the minus 21. That's the strain, right? That then tells you that we know what the intrinsic radiation, because general relativity tells you that is. Then you can just use this 1/d scaling that we've talked about before to get the distance, again with some lots of imprecision. So and so the parameter, there's a whole team of people in LIGO that do nothing but try and refine the estimates to the way we measure the gravitational wave parameters. So that may have been a little long-winded. If I had a picture up here, I could show you a little bit more, but
Yeah. So you're comparing the waveforms to a library of pre-calculated waveforms from theory.
Exactly.
And that's how so the more pre-calculated waveforms you have, the better you can do.
And we have millions of them. I think right now we use 1 million. And one more thing to say, the other aspect of that, particularly with the distance, is that equation that I showed you. If you have a source that's a distance d away from you, the amplitude of the wave decays as 1/d. So once you know what the source parameters are, you use the amplitude of the wave to give you that D. That's the key right there. Now let me point out something else. Again, what happens if we don't know the waveform? And if a supernova explosion were to happen, for example, we don't know how to calculate that waveform. All right, so there the calculation gets a little trickier. And the estimation of parameters gets a little trickier because we don't have a theoretical model that we can fall back on. So
that's where you really need coincidence with an electromagnetic event.
Yeah, or neutrinos or something like that. Exactly. Yeah.
Cool.
Excuse me, other questions?
I'm assuming that once detectors, the larger detectors are online, that you'll be able to see more gravitation or see gravitational lensing events.
We hope so. I mean, you can, as I said, I think I was talking about this earlier. The rate of gravitational waves lens events is not very high. All right, so the rate of gravitational wave signals, we're getting better at detecting them. So in the last run, we were able to detect, I think, 1 every 6 days on average. So we're actually getting good at this. The next, we hope, with the upgrades that we're doing, we'll be seeing an event 1 every 2 days. That's the events we see. The rate of lensed events is a tiny fraction of that. So maybe 1/1000th of that. So you've got to run for a long time to see, have a chance of seeing a lensed event. But these future detectors, the rates of detection will be measured in these events these detectors are so sensitive that we'll see thousands of events per day. I mean, basically an event every few seconds. All right, and there, the rates, even though the rate's small, you've got so many numbers coming at you that you'll probably be able to see it. So.
Plus, you'll be getting more signal coming from behind galaxy superclusters and stuff.
Right.
So
Right.
That was my point.
And because the sensitivity is better, it means you can see further out in the universe. So the rate of events just goes way up. Yeah.
Well, Dr. Reitze has been very gracious with the time he has spent with us. Thank you very much. We probably need to start winding the meeting down. I'm sure there are more questions, but let me point out, we may have just scratched the surface on this subject, but Dr. Reitze, with his collaborators, has written a book that describes the entire domain of gravitational wave science and engineering. You can find out all that you would want to know in the book titled Advanced Interferometric Gravitational Wave Detectors in 2 volumes by World Scientific. I'd like to be able to tell you that you could log on to Palomar Observatory's gift and bookstore and order this work online, but we haven't been able to put together a sales agreement. So the book is available from the publisher and, of course, through Amazon and other outlets in Kindle and hardcover editions. I'd like to conclude then with a few words about our next speaker. In 2 weeks, on August 24th, Dr. John O'Mara, Chief Scientist at the W.M. Keck Observatory, will give a talk titled Spectroscopy, How Astronomy Really Gets Done. And you should know that one of Dr. O'Mara's colleagues has supplied an alternate title for this talk, Spectroscopy, Why Astronomers Don't Really Care About Pretty Pictures. Well, I point this out to alert you to the fact that in a few months, Sultan Levay will join us and he will tell us why pretty pictures of the cosmos are of the greatest importance and why they serve an iconic function that we all ought to care about very much. And with that, again, thank you, Professor Reitze,
Thank you.
and thank you to everyone for attending and supporting the Greenway Talks online. We'll see you next time, and with that, I'll close the meeting out. Thank you to everybody. Please come again. Everybody wave.
Outstanding.
Take care, all.
Hey, bye-bye.
Bye.